My name is Kazwan Abdullah, and I'm going to present about a brief survey and investigation of hyperperforming for millimeter wave in 5G massive MIMO system. This slide contains an introduction to millimeter wave massive MIMO system, the objective, the system model, the simulation result, and conclusion and references. A brief history of cell phone. In the first generation of cell phone in 1970, it was an analog phone. Then the cell phone keep improving to G. It was a digital phone in 90, and the cell phone keep improving in third generation in 20. It was like a MIMO HSBA system using a pocket switching for data. Then the cell phone keep improving in 4G in 2010, WiMAX, LTE, IP address. It was like a small computer in our hands. And the 5G now is expected to increase the capacity to and the speed to 100 times like 4G. Hyperperforming in 5G. The goal of hyperperforming hyper analog digital transceiver architecture is to introduce analog signal processing component between the power amplifier and up converter at the transmitter side. It also introduced another analog signal processing component between the noise amplifier and down converter at the receiver side. This approach can expect and reduce the power consumption of digital signal processing unit, analog to digital converter, and digital interfacing card. Hyperperforming in 5G. The hyperperforming techniques that reduce required resolution of analog to digital converter. Transmission is became like more directional between the base station and cell station and users. Can be visualized at a laser beam. The higher density of the beamforming leads to the less interference and less energy consumption. Faster data rate can be achieved. Here in this graph, we can see the millimeter wave, which from 30 gigahertz to 300 gigahertz. The proposed for 5G ring from 24 to 100 gigahertz. And we see here the very crowded area from 1 gigahertz to 6 gigahertz. We hear the GPS, WiMAX, all the devices here. Millimeter wave with the small cells. Due to that, millimeter wave lose their energy very fast and only suitable for short distance, so they need a small supporting small cells between the active users and the base station. So in the future, maybe we'll see a lot of base station. Millimeter wave spans, as you see, from 30 gigahertz to 300 gigahertz, deploying the massive MIMO antenna. Higher frequency wave carry more data than lower frequency. That's why the millimeter wave boosts the capacity of the 5G. The higher frequency wave use the smaller antenna we get. That's the make the millimeter wave is a good choice for massive MIMO. One small cell can handle many users at the same time. At the same time, the higher frequency have more collision with the obstacles, and that's why they will lose their power very fast. It tends to lose energy more quickly. Millimeter wave signal cover the short distance. A small station is needed to fill the gap between the base station and the users. The massive MIMO features, we have massive, very large transmitter receiver, high data rate, more signals path, complexity increase, more energy consumption as the number of antenna increase, both the channel capacity antenna site is reduced. Introductions. We keep doing the introduction about the millimeter wave. The massive MIMO system, which exploit a huge number of antennas at the base station to assist 10 or more hundred users' equipment. Millimeter wave is a promising technique to enhance the network capacity, a covering of the next generation based on utilizing a great number of available spectrum resources in mobile communication. You see here the small cells, and you have see the base station. You see here. This is the system of 5G millimeter wave. The problem statement is the RF chain is the key practical power consumption circuit, where is the transmit power increase proportionally with the number of antennas. The large number of antennas increase the cost of both efficiency and wireless network. We can see in this system we have here the transmitter, we have the digital to analog converter, and we have RF chain which connected to the antennas. Due to the phase shifter, to reduce the power consumption of RF, we have to reduce the number of RF chain to reduce the power transmitted power by using the soft selection method or hard selection method. Here we have the receiver side, we have analog to digital converter and RF chain, and this is the system. We combine the analog and digital converter, so we get the accuracy of digital, and we can also reduce the power consumption. The objective to investigate a low-cost power consumption by providing the optimal low RF chain in a small cell based on the state of considerable power and controlling the distributed power from millimeter wave. The system model we have here around 14 equations. The transmitting the signals through the channel. The path losses decrease the power density, can be expressed in equation 1, and the proposed in propagation medium, the power in the propagation medium for distance and wavelength can be written in equation 2. The power gain here, this is the equation for power gain. The signal to noise plus interference ratio transmitting from the base station to the active user in equation 4, and we have the data rate for use can be used at equation number 4. The equation 5 and 6 and 7 and 8, it is optimal beamforming for dense small cell can be improved depending on the real time for total power consumption to achieve the quality surface. This is the question 9 and 10 when you use it in graph 2, our result. So in order to reduce interference in a small cell based on the minimizing the transmitted power signal and the quality of surface can be used using this equation 9 and 10, where here we have to decrease the circuit power consumption as the result of using several transmitter antennas as a model power dissipation for free antennas such as converter from analog to digital or digital to analog mixture filters. You use this equation 11. The high energy efficiency can be obtained by decreasing the distance in dense small cell between the active user and base station, reducing the high cost and the energy consumption in order to obtain the minimum transmitted power. You see the equation as you can see in the graph 1. Signal to noise plus interference ratio, SINR. Analog to digital unit contains a weak desired signal and a strong interference signal as a result of lower SINR input signal. The larger number of antennas has a smaller number of SINR. Receiver signal experience small SINR at the input unit of each analog to digital converter if the number of antennas is large. The numerical result, we can see here the high cost and large hardware complexity could be improved by avoiding devoting and connected RF chain for antenna based on employing massive MIMO baseband recording in dense small cell by employing sufficient multiple antennas for massive MIMO system turns. You can see from this here graph the relationship between the quality of service for users and the power transmitted. The power transmitted increase by increasing the number of users. So we have here a techniques which we call optimal performing and propose low complexity and optimal dense small cells to reduce the transmitting power. The energy efficiency in start to increase when the maximum SINR is high by guaranteeing each active user connected with only one base station to avoid affecting the user association and reducing the transmitted power, while the energy efficiency start decreasing when the number of antennas increasing, which require a guarantee of low cost and low power based on providing a load balancing probability in order to increase the energy efficiency under the constrained power and control and the quality of surface requirement, as we can see in the figure in equation 9 and 10 for this graph. So as you can see here, the energy efficiency is became less when we increase the number of users. It was about 28 when the active user is 15, but it reduced to about 25 when the active user 20, and be reduced it to about 22 when the active user is 20. This is a relationship between the number of antennas and the energy efficiency. So increasing the number of antennas decrease the energy efficiency. Conclusion, the hyper-beamforming can improve the channel and choose the minimum number of RF chain, reduce the hardware complexity, and use the huge number of transmitter antennas. Reducing a large path losses in the relay fading channel based on improving the hyper-beamforming in millimeter wave can exploit a large bandwidth. Thank you and see you in the next conference.